Hey everybody, this is Larry, this is me going with Q4 of the bi-weekly contest 128. Find the number of subarrays where boundary elements are maximum. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. This one, I've heard that there are a couple of ways you can do it, and there probably are. I did it with the idea that I've been talking about, I think 2 weeks ago maybe, but also it is kind of the a little bit of a hint is that it has been what we've been working on for the daily problems. So it's kind of a little, I don't know, this feels a little bit yucky to kind of be that way. But as a result of that, I have had more practice than I would have normally. But the idea that I would think about is just this idea of contribution, right? So what do I mean by that? I've said this before, and on the sliding window bit, like I said a couple of weeks ago, so you should watch me every day. But yeah, the idea here is that looking at each element, I go, okay, we do, n is 10 to the 5th, of course it is, otherwise it's just n squared, and this is a very dumb problem, or maybe not a dumb problem, but a dumb Q4, because it could be a Q2, I guess, if it's n is like 100 or something, right? But the idea with contribution is just that, okay, let's say this element is the last element of a subarray. How many subarrays are there? Valid subarrays. And this is what I call the contribution to the answer, right? How many subarrays are there? So 1 is going to be 1, 4 is going to be 1, 3 is going to be 1 because there's nothing to the left of it. And then 3, then now there's 2, right? Because you could choose between ending it here or here. 2 degrees of freedom, 2 answers, and there you go. And then 2. Okay, but this example, I know that they did it to be dumb, right? Or like they don't want to give anything away or give you hints, right? And this is 3, 3, 3 as well. It's also like it's a good case that they give you, but also, like it's not meant to give you any more ideas. So I think these are actually very good example cases. But yeah, same idea with 3 is that 3, you have 1, right? And then here you have 2 because you could you end at here. You could start at here or here. So there's 2 choices to start. Here you end at here. So you have 3 choices to start. So it's going to be 1 plus 2 plus 3. So that's going to be 6, right? So contribution is the idea behind this problem. But you have to figure out how to get that quickly, right? So the biggest thing that I thought about was like, let's say you have something like this. Well, okay, fine. Well, in this case, the 4, you cannot connect the 4 anymore, right? So at this 4, you only have 1 contribution, and I think in this one, the answer is like 10 or I guess 9, right? So then the idea here is, what do you do? So the way that I did it is by using a stack. By trying to find an invariant, right? An invariant is that there is this cutoff where you can't go to the left anymore. But also, what does that mean? That means that you're trying to get in another way. So if the current element or last element is X, we're trying to get the last element that is X, maybe a little bit more, without any number greater than it, right? So that's basically the core part of the idea. And the invariant is that, well, that the idea that I started was with a stack, right? So let's say I have 1, and then now we have 2. Well, if we have 2, we look at the answer 1. This is the stack, right? If we have 2 and we look at the previous answer 1, well, anything 1, like if we have any 1s to the right of 2, it doesn't matter anymore, right? Because it cannot go past the border. So that means that we could get rid of this 1 because it'll never show up as anything useful again. So now we have 2 on top of the stack. Let's change this around a little bit so we get actual answers. But yeah. Right? And here, same thing with 3, right? But then now we have a 1. We go, okay, well, 3 could still be a future answer, right? So we want to keep that 3. 1 could also be a future answer, so we want to keep the 1. So the stack is now 1 on top and 3 on the bottom. Same. Now that we look at the 2, we go, okay, 2 is no longer the possible answer to the left. Or sorry, 1 is no longer possible to answer to the right, so we get rid of the 1, but 3 still can be, so we kept the 2, right? And then now we have a 4, that clears everything up a little bit, right? Because now the 2's and the 3's and the left and the right doesn't matter, right? And then you have a 2, and then now the 3 again, and then now you have a 4, and then you have a 4. Oh, and then this 4, you go, okay, now we match the last 4 so that we can add that number in, right? And then now we have a 5, and the 5 means that all the 4's cannot be used as an answer to the right in the progression. So then now we get rid of it. And then now we have a 4, we have a 3, we have a 2, and a 1. That's basically the idea. I don't know that I described it that well, but the idea here is finding that invariant where your stack represents all the numbers that you can care about, right, in the future usage of it. And it turns out, of course, you see this a lot, where this turns out that because of the way that you arrived at this, it turns out to be quote unquote a monotonic, well, this is monotonically decreasing stack, which is a monostack, but I never think of it in terms of monostack because that's just a name that is useless to me, right? What I want to figure out is this relationship, this invariant of whether, or like, how useful are the things that we keep on the stack, and why is it that only the top of the stack matter? Well, only the top of the stack matters because it gives you all the numbers that are smaller than it. So the top of the stack is the smallest number that you care about, and you get rid of them as you move on. So that's basically the idea. I did add a little bit of trick here, additional trick, which we'll go over in code. But that's the idea. Here, I set the top of the stack as infinity, so that will never match. But yeah, first we pop off the stacks. If it's smaller than x, then we pop up the top, so we never pop this. I don't know, right? And here, if the top of the stack is equal to x, which is our current element, then now, the two things that I know that in this stack I just chose the number, and in this case you can have 4, 4, 4, 4, 4, or something like this, and it will be very expensive to count. Maybe you could do a binary search, I guess, but the way that I did it is I just do compression. So here, if I have 4 4s, I would just convert it to 4 5, right? And then maybe like 3 1, 2 1, and so forth, right? Dot. So then now it tells you that there are 5 4s in a row, and that also gives you the answer because that's the number of 4s that you can choose if you have a 4, right? So let's say you have a 4 coming in. Now this is useless, so you remove it. And then now this is the last element. You could choose any of the 5 previous elements as the beginning, plus the current one, so it's going to be 6, and that's how I wrote it. And actually, you could probably win, I could win it like this, and then something like that. I think maybe that's a little bit cleaner, I don't know. Yeah. Make sure that it works. Alright. But basically this is saying that, okay, the count is 1 for us to push to the stack. If it is the same as the stack, then we just push it like in here. Instead of creating an extra 4 1, we just convert this to 6, right? So this is just like that kind of merge. And we also pop it so that we can push it back on the stack equally. And here, this is the total. This reflects what I call the degree of freedom, which is the number of choices you have as the first element, and then you just sum it all up. And that's pretty much it. This is going to be linear time, linear space, and yeah, that's pretty nice. There are also other solutions to this that I'll talk about really, really briefly. I think that another idea here is that that I think Gia brought up when I was playing around with it, is that you can kind of sort these in a way such that you parse them in order, right? In the value order. So for example, you process all the 1s first, and then the 2s first, and then the 2s, and then the 3s, and so forth. Because then now you do this one, right? And then they're just elements because they're not next to anyone, right? And then I'm just gonna remove this 3 just for easier illustration. But yeah, and then next the 2's. Well, the 2's then now you can merge to the left, merge to the right because 2 is bigger than 1. And then when you go to this second 2, you go okay, merge to the left, and then now you see that you could do it that way. It's a little bit trickier, I think, but you can do it that way as you scan up and merge things along the way, right? But I don't know. I don't there are different ways of doing it. Play around with that one, and it requires other data structure as well. So you may need to know more stuff about this one. But yeah, the stack is how I did it though. I just want to bring it up so in case you want to practice doing it another way. That's what I have for this one. Let me know what you think. Stay good, and you could watch me solve it live during the contest now. Sure, that would have been a very silly mistake because it's an example. If it wasn't an example, it would have been fine, but alright. People already finished this. This is ridiculous. Okay, fine. I don't know how to do this yet off my head, but shouldn't be that bad, but trying to be careful. The examples are not great intentionally, but 2 inputs. Huh, okay. Well, this one, that's fine. How's that? 3. 1, 2, 3, right? What am I doing? Oh, whoops. Should be 3, okay. Okay. It wasn't that bad, but I had to verify the results. Thanks for watching, everybody. Thanks for the support. Yay! Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this prompt, explanation, description, this contest, everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.